No, fair. He doesn't believe in like partial credit or something.
Oh, yeah.
Okay.
True.
All right, let's get started. Let me get the sign-in sheet passed around. I do not have your exams graded yet. It's going to take a little bit more time. Let's just say we'll figure something out. We'll figure something out. Don't worry. We'll figure something out. I'm going to leave it at that. I don't have much in the way of major announcements past that. We don't have an exam scheduled here until after break, okay? But the exam that we do have will be on the Wednesday we get back. So Monday we will have our review, and then Wednesday we will have our exam. And what I'm going to do for that exam is it's going to be on T-beams, it's going to be on doubly reinforced beams, and it's going to be on shear. Okay, that's what's going to be on the exam. So homework's 5 and 6. So you currently have homework 5 now, and that's due on the 11th. So you've got a lot of time on that. In fact, there's only one problem that you can't do on the homework as of right now. Well, I mean, you could go ahead and go through the notes and whatnot and attempt it yourself, but really it's the last problem. And so that's kind of what I want to cover today, is I want to talk about doubly reinforced beams. They take a little bit of discussion. They're not all that difficult. I mean, they end up being kind of plug and chug, but I kind of want you to understand what you're plugging and chugging and why you're, what you're doing and why you're doing it. So let's just sort of dig right into it, and let's talk about doubly reinforced sections. Let me get. There we go. Okay. Now, when we discussed T-beams, what made T-beams sort of complicated, if you will, was the fact that there's 2 cases of analysis and ultimately 2 cases of design. And that is whether or not your T-beam is a rectangular T-beam or whether or not it is a true T-beam. Okay? And the difference is the shape of your stress block. A very natural topic that comes after T-beams is a doubly reinforced beam, because like T-beams, there are 2 cases of analysis. Now again, what I'm talking about with a doubly reinforced section is I'm talking about a section that has steel not only in the tensile region, but steel in the compressive region as well. So that's what we mean when we say doubly reinforced, is that there's steel on the bottom and on the top. Bless you. Now first off, I guess the question is, why would you consider this? I mean, when we're talking about beams of normal proportions, generally you don't need to put steel in the top. Remember, concrete is a material that behaves very, very well in compression. So adding steel in the compression region usually isn't all that necessary. And so much so that when we're talking about this from a class standpoint, I actually don't really care about your ability to design a doubly reinforced shape. I really only care about your ability to analyze it. The only time you would ever desperately need to put compression steel in from a design standpoint is if the size of the beam is restricted. Like you've got some really strict architectural requirements, and there is no way to get that beam stronger. You could add some compression steel. And when it comes to design, and we're starting to talk about practical concrete design in the field or in professional practice, I don't know that I'd really develop a design procedure. I just build a big spreadsheet and say, well, if it doesn't work, add 2 number 4s, add 2 number 5s, add 2 number 6s until I got it to work. That's the beauty of something like Excel. You can just sort of tweak it until you get it to work. Now, there are some reasons, if you will, for considering the compression steel from an analysis standpoint. I'm a popular guy this morning. Let me turn my phone off. First off, adding compression steel reduces the long-term deflections on the beam. Now, I'm going to be honest, that doesn't really make a lot of sense right now, but that will later. But suffice it to say that when we look at deflections later, just to introduce the topic, there is a difference between the deflections that you get in a beam on day 1 and deflections that you get in a beam 5, 10, 15 years after it's been in service. The thing about concrete is its mechanical properties, its resistance to stress and strain, they change over time. Okay? Concrete is sort of a living material in that regards. Steel sort of isn't. Steel, as long as it's not subjected to significant corrosion or anything like that, steel kind of behaves how steel's going to behave regardless of time. But concrete properties change. And so the deflections on day one are different than the deflections in the long term. And so if you put compression steel in the beam, that can affect and improve a beam's long-term performance. Two, you tend to put steel in the top of the beam anyways to support the stirrups that go around this set of rebar, and we'll use stirrups to improve the beam's shear performance. In fact, when we're designing for shear, it's about laying the stirrups along the specimen. But more often than not, if you want to consider the compression steel, it tends to be there anyways. Again, at the very least, you usually put 2 bars up top to tie those stirrups together. So that's sort of why you would consider it. You probably, in most cases, don't really need to design for it. But one of the reasons I like this topic is because it really does, no pun intended, it really does reinforce your understanding of just some of the fundamental concepts that we've been discussing about stress and strain and things like that. So what I want to do is I want to look here. I've got this on the slide. I also have it up here on the board. I want to introduce some new notation. Okay? Remember, I'm really trying to be cognizant that all of my notation is consistent, and I'm doing the same thing here. So much of what you see here is what you've seen before. The beam is, let's say, B wide. We could say it's H tall. But, you know, when we're talking about capacity, we really haven't cared so much about H. What we've cared about, sorry, this is, I have a typo here. What we've cared about is D. Okay, the distance from the top of the beam to this steel right here. Well, now we're going to have a new layer of steel up top. So instead of A sub S, I'm going to call this AS prime. And then instead of D, I'm going to say from the top of the beam to the center of this steel, we're going to call that D prime. Okay? So anytime that I have a prime on a symbol, it's going to refer to this layer of steel, this compressive layer. Anytime I don't, it's going to refer to the tensile layer of steel. So I want to make sure that we're aware of that. Now, what makes the analysis of a doubly reinforced beam complicated is really all about this layer of steel. Okay? Now, I want to investigate that discussion. By looking at this. Okay? What I have here is the strain profile on the beam. Right? Remember what the strain profile is. Right? Remember you have a book and you bend it and it sort of behaves linearly. Remember that code I brought in? You take a Sharpie and draw a straight line, you bend it and it stays straight. So what do we have here? Remember, this distance C is the distance to the neutral axis. The neutral axis is the point in the beam where it doesn't deform at all, right? Everything above the neutral axis, it compresses. Everything below the neutral axis, we see the beam in tension, right? Okay, and so what do we do here with our strain profile? Well, we recognize at the very, very top, the maximum usable strain is 0.003. And so let's do something that we've done before. Okay, so before, what we did is we looked at this and we looked at it from a similar triangles perspective. And we said, okay, 0.003 is to C as whatever this term is to D minus C. Remember that? So this is to that as this is to that. And then what did we end up saying? Epsilon sub S is 0.003 D minus C over C. All right? Does everybody remember that? We've been using that formula for the past few weeks. I just want to make sure that everybody remembers where it came from. Okay? Well, just as we determined the strain in the tensile steel, now I want to develop an expression for the strain in the compression layer of steel. Okay, so how do I do that? Let's see if we can do that. So 0.003 is to C as what? So 0.003 is to C as epsilon sub s is to what? Well, I guess I have this drawn, this is sort of drawn incorrectly because I really don't care about this distance. What I care about is, I guess what? This distance? Right? What do I have here? I've got 0.003 is to C as this strain is to what? What is that distance? What is that? So what am I doing? I'm doing this is to that, is this is to that. What is that distance? Somebody help me out.
It's C minus D prime.
C minus D prime. Yes, so this is C minus D prime. Yeah, I had already labeled this over here. So this is C minus D prime. So therefore, the strain here is 0.003, but instead of D minus C, it's C minus D prime. Is that a fair statement? Is everybody okay with that? So I've got these two expressions here. I've got this expression, and I've got this expression. Okay. So is everybody okay with that? Just, I mean, let's ignore what I've been saying earlier about the different cases and all the different challenges with the analysis. Do you agree that if I gave you a beam that you could determine the strain here and the strain here? Right? Is everybody okay with that? Now, why am I bringing this up? Why is this an issue? Okay? Well, here's why. Okay, so I have here in my next slide, that's just me doing this. But let's talk about these strain values. Okay? Now, remind me, let's recall. So the strain at yield is Fy over Es, right? And so for grade 60, anybody remember what that was? It was like 0.00. Well, no, that's the limiting strain. This is the 0.002. Right? Now, but let's go on with that discussion. Now, why did all these strain values matter before? Why did we compute this before? Why did we ever compute this value? I'm asking.
See if it yielded.
To see if it yielded, right? But not just to see if it yielded, but what was the thing? It had to yield, right? Wait, we say that this has to be bigger than that plus 0.003, right? So it is actually an ACI requirement that the tensile steel yields. It has to yield. Here's the problem. Nobody said this had to yield. Nobody said this had to yield at all. So where does a doubly reinforced beam get complicated? Well, it gets complicated because you have two potential cases. One where the compression steel yields, and one where it doesn't. Okay? And when it doesn't yield, that's when it gets a little complicated. All right? So let me skip this next, or let me hold off on this next slide, because I want to explain what happens when the compression steel yields and when the compression steel doesn't yield. Okay? Now, ultimately, regardless of what we determine here with these yields and these strains and all this stuff here, we ultimately perform the analysis of a beam by assessing what? Compression equals tension, right? I mean, how do we determine the depth of our stress block and all that stuff? We do it based off of C equals T, right? So what that means is that we need to determine compressive forces in the concrete, compressive forces in that upper layer of steel, and a tensile force in the lower area of steel, right? And C's got to equal T. Fair statement? So let's see what we can fill in here. What's the compressive force in the concrete? Well, it's a rectangular beam, so 0.85 FC prime AB. That doesn't change. What about the tensile force in the steel? This has to yield, so ASFY. But this one, that one's a little unique. Let's talk about that. Remember the stress-strain curve, right? Arguably one of the most common curves that we use in structural engineering. Well, for metals, for steel, what we're doing in our analysis is we're assuming that the curve is linear up until Fy, right? So this is Fy, this is our yield strain, and that is the Young's modulus. Put this out of the way so you all can see what I'm doing. So far, so good? So, there's really two cases. If the compression steel yields, then the stress is just the yield stress. And the compressive force is ASFY. But what if it doesn't yield? And I have all this stuff in the slides, but this is one of those lectures where I kind of think it behooves us to actually take our pens in our hands and write it down. Doesn't. So if the compression steel yields, the force is pretty easy. But if it doesn't yield, then I propose that the stress in the steel, instead of being Fy, is going to be E times the strain. In other words, if my strain is smaller than that, then the stress is just the slope times the x value. It's just y equals mx plus b. But what is this? So this is that's that, right? So the compressive force is I want to digest that for a second. Does that make sense? Does that make sense? So, again, I have all this written in the next slide, but I want this to make sense. If the compression steel is yielded, then the force is just ASFY, or AS prime FY. But if it hasn't yielded, what happens is my compressive force is the area times the stress. And the stress is E times the strain. What's E? Burned into the back of your head. E for steel is 29,000 KSI. It will be burned into the back of your head by the time you're out of here. That term's 29,000 KSI. So the area times the stress is E times the strain, and the strain is what we just derived. And so if we have a situation where the steel hasn't yielded, we say that C equals T. So if it has a yield at C equals T, so all the compressive force plus all the tensile force, set it up in one big equation. Look what I did right here. Look what I did right there. Instead of 0.85 FC prime AB, I said 0.85 FC prime beta 1 CB. Why? Because A equals beta 1 times C, right? And the reason I did that is because if you rearrange the expression, you know, this is just from here to here, this is me just doing a little bit of algebra. What do I have? I got a pile of junk times C squared plus a pile of junk times C minus another pile of junk equals 0. It kind of looks like a quadratic equation. So if your compression steel doesn't yield, what you've got to do is you've got to solve this quadratic equation to solve for that, to solve for how deep is the neutral axis such that compression equals tension. Does that make sense? That's a little bit wild, I know. This is a new one, so I want this to sink in. Any questions? All right. What we're going to do is this. We're going to do two examples, one where the compression steel has yielded and one where it hasn't, and I think you'll see what happens. I promise you that in practice this really isn't very difficult. It's pretty straightforward, but I really want you to understand the ideas. And if anybody is curious, I thought I should mention this. We are way past what you would have to deal with on the FE. ASFYD minus A over 2. That's literally all that's in the manual. So if you can do this, you are fine for the FE, I promise you. Now, I have this example. We're going to determine the design flexural strength. So we're going to determine phi mn of this beam. I got 2 number 9s, 4 number 11s. So I've got an AS prime and an AS. Notice that my D prime is from the top to the compression steel, 2.5 inches. From the top to the tensile steel, that's D. That's 24 inches. B is 14 inches. I gave you H. I said H is 27 inches, but quite frankly, I don't care what H is. Because that doesn't matter. So let's just sort of get right into it. I like this topic because it truly is a test of pretty much, oh goodness, truly is a test of just about everything that we've done so far. So, okay. So to start off, we know that FC prime is 3 KSI for this problem. So that tells us that beta 1 is what? Come on now. There we go. I'm going to start calling on people, I promise. You watch me. Just wait till we get to shear. Alright, so Fy is 60 KSI. So what I'm going to do here is I'm going to go ahead and compute my strain at yielding, which is Fy over Es. So 60 KSI over what? All right, you're good. I'm going to start calling on somebody else. And it's going to be the folks that as soon as I look to the class, you're like, those are the ones I'm calling on. So just watch. So this ends up being about 0.00 what? 2. You can say 207 if you want to be super accurate. And then our limiting strain is this plus 0.003, which is 0.00507. So we'll need our limiting strain in order to determine phi. Okay, so that's why I went ahead and did that. Okay. Everybody with me so far? Okay. Now, the way that you analyze a doubly reinforced beam, what's the simpler case? If it yields or if it doesn't yield? Just if it yields. If it yields, this is easier. Okay. So what we're going to do is we're going to assume that the compression steel yields, okay? And then we're going to see whether or not that assumption is valid. So let's assume over here the compression steel yields. Okay. So if the compression steel yields, what we're saying is the compressive force in the concrete plus the compressive force in that upper layer of steel has got to equal the tensile force in the lower layer of steel. Now, let's fill out each of these terms. So the compressive force in the concrete is the same as it always was, 0.85 Fc prime times the area of the stress block, which in this case it's B wide and it's A tall. So, we'll talk about that here in a second. So 0.85 Fc prime AB plus the compressive force in the upper layer of steel, the area of steel up top times Fy equals that. So what do I have? This is C sub C, that's CS prime, that's TS. If you want to write that down. I actually don't. Now, I want you to look at that equation and I want you to tell me, what do we not know? A, it's the same story as before. We know the areas, we know the material, or the areas of steel, we know the material expressions, we know B, we don't know A. So, how do I solve this for A? What do I do? Drag that over, right? So, what do I have? AS Fy minus AS prime Fy. Factor out the Fy's. Divide by all that, so what do I have? I got A equals AS minus AS prime Fy over that. Does that make sense? Did I go too fast with that? They got a number for me?
7.14.
7.14. Do I have a second on that? Was it 142 or what's?
143, I guess, if you round.
Let's do one more. I kind of like to be specific at this point because in order to verify our assumptions, we need strains, and strains are really tiny values, so a little bit of specificity is probably a good idea right now. All right. Now what I'm going to go ahead and do is, let's be clear, in order to verify our assumptions, okay, what I need are strains. These are my formulas for strains. What am I missing? What's in these formulas that I don't have? C. So I computed A so I could compute C. And I computed C so I could get those. So C equals A over beta 1, 7.143 over 0.85, which is what? 8.4. I think it's like 03. Again, right here, a little. Make sure you're a little specific. Like I would go to like 2 or 3 decimal places here, because you want to be accurate on these strains. These strain measurements can be a little sensitive. Sound good? Okay. Now, in order to determine whether or not the compression steel yields, it all hinges on this, the strain in the compression layer of steel. So let's compute this. All right, so therefore, we have the strain in the upper layer of steel, 0.003 C minus D prime over C. So again, I'm being real cognizant to ensure that I'm using the primes correctly and whatnot, because this is where, like when you're on an exam or doing a homework, that you put in D instead of D prime and the numbers don't make any sense. Okay, so make sure that you're really cognizant on that. So 0.003 times 24 inches minus 8.403, 8.403.
Where'd you get the 24 inches from?
Oh, see, there you go. I'm messing it up. I literally just said don't do that, and then I did it. You're exactly right. That's 8.403 minus, what is D prime?
2.5.
Thank you. See, anybody can do it. Me messing it up just there is a perfect example. Thank you. Since you pointed out an error of mine, I'm going to be taking more points off your homework assignment.
Should have just played it off. I played it on purpose.
I'll admit it, but now he's going to suffer. You know, come on. I'm not that mean, am I? All right, what do we have here as an answer? Let's do 5 decimal places. Let's be pretty specific here.
.00211.
Okay, do I have a second on that? Okay. Let's take a second. What can you tell me about that strain value? Let's ask it another way. We assumed that the compression steel yielded. Did the compression steel yield? What is the strain required to yield the compression steel?
0.002.
0.00. So what you can say then, so this is 0.00211. The strain at yield is 0.00207. Did it yield? Yes. So our assumption that the compression steel yielded is valid. The strain is higher than the strain required to yield it. Again, this is so going off our curve here, this is the strain at yield, and our strain was like right there. So our assumption was valid. So what we'll say is sound good? Now, since I'm in a good mood and we're computing strains, I computed the strain in the upper layer of steel. Why not, just for the heck of it, compute the strain in the lower layer of steel? Now I can use the formula I was doing before. Here, I'm going to mess around with my drawing here on the board a little bit. Make it a little simpler. So anybody got an answer for me? 0 point something. Somebody's got to have an answer. Not here.
0.0557.
00557. Do I have a second on that? Okay, so here's our string profile. So what we're saying is, let's just look at the numbers. Okay, so this is 0.003. So one way that you could check this is to see if this makes sense. This is 0.003. This came out to 0.00211. This one came out to 0.00557. Right? Okay, so obviously that's got to be smaller than 0.003 by a little bit, and so on and so forth. Okay, now this came out to 0.00557. What can that tell us? Why did we compute the strain in the steel, the lower layer of steel before? Like, why did we ever compute that?
Fee value.
The phi value. And so what do? What do I compare that against?
0.00507.
So the limit. And what can you tell me about this observation? Well, we know that the strain is greater than the limit. What does that mean? No, well, yeah, it means it yields, but again, why did we compute this strain to determine what? Come on, everybody. I mean, he just said it. We compare these two for phi. What does this mean? Phi is 0.9. There we go. I know y'all know this. Remember. Yes.
So, I might know the answer to this, but I just want to ask it anyway. Why do we compare the ES prime to yielding, but the ES to the limit?
Okay. Because they're two different comparisons. Okay. We're comparing this to the yielding strain to verify our assumption. Okay. All this math that we did up here, all this math in this blue box, all of this assumes that the compression steel yields. I don't know if that's true until I look at the strain in the steel and compare it against the strain yield. Okay? So what am I doing here? I'm verifying this assumption. That's why I'm making this comparison. Now, why am I making this comparison? I'm making this comparison because this is the same comparison I've made for the past 4 or 5 weeks. I look at this strain value here and I compare it against the limiting strain. This ACI requires that this strain is larger than the limiting strain. So not only am I verifying an ACI requirement, I'm verifying that phi equals 0.9. So why am I making the two different comparisons? For two different reasons. All right, does that make sense? I'm getting some puzzled looks. Are we good? Okay. Again, don't hesitate to ask if you've got questions. That's what we're here for. All right. Now, what do I do from here? First off, let's look at equilibrium. So we have our compressive force in the concrete, 0.85 FC prime AB. So 0.85 less than 3 KSI. What was A? I don't remember that.
7.143.
7.143. And what was B? Was it 12 inches?
14.
14. What does that come out to be? 255. Do I have a second on that? Okay. How about that? The compressive force in that upper layer of steel. Well, what do we have? Compressive force in the upper layer of steel is this times Fy because this assumption was true. Okay? So, and so what does that come out to be? That's, well, if I can do that in my head, that's 2 times 6, that's 120. And TS is ASFY. What was AS? Was it 6 something?
6.25.
I'm not that good.
375.
So, note, C sub C plus CS prime is 375. Compression equals tension. A verification that equilibrium has in fact been met. All right. So far so good? Okay. Now, the one thing that we have yet to do is we have yet to determine Mn. We have yet to do that. Now, do y'all remember how we did that with the T-beam? What did we do? We split it up into the flange couple and then the web couple when we were dealing with the true T-beam. Y'all remember that? We're going to do the same thing here. Okay? What I'm going to do here is the following. So, let's see if we can illustrate that. Hold on. So, I've got this. Right? So this dimension is A, that's my stress block. That dimension is B. That's D prime. That's D. Okay? Excuse me. What I'm going to do is I'm going to say, all right, it equals this plus this. Same story as before. How do we define a moment? Just basics. It's a force times a moment arm, right? Okay, so let's look here on the left. The force, we're going to say, is C sub C. But what about the moment arm? How do we define that moment arm? Well, bless you. This dimension is D, and that dimension is A. So remember, what are we doing, right? We're saying I've got a force this way, a force that way, and I'm after that moment arm. So how far is it from the center of this force to the center of that force? Should be a pretty simple one. D minus A over 2. Now, how about this one? Our compressive force is AS prime FY. Well, actually, I mean, we can, to keep it simple, we already computed this, so we can just, just recognize that it's C sub C. What about our moment arm? I'm curious if anybody can tell me what this moment arm is going to be. How far is it from the center of that to the center of that?
D minus D prime.
D minus D prime, exactly right. Because this dimension here is D, that dimension is D prime. So how far is it between the two? D minus D prime. So, what is the moment capacity of a doubly reinforced section? It is C sub C times D minus A over 2 plus CS prime D minus D prime. And one of the things about this formula actually holds true for both cases. The only thing that's different is what that is. But in the end, that formula works because the compression steel doesn't move. The shape of the stress block for the concrete is still rectangular, regardless of which case that we're looking at. So this formula actually holds for both cases. Does everybody have all this? So, therefore, Mn is C sub C, D minus A over 2 plus CS prime, D minus D prime. So C sub C was 255 kips, 24 inches minus 7.143 over 2 plus 120 kips. 24 minus 2.5. Anybody have an answer for me?
$77.89.3.
7789.3 what? The moment. Inch kips. So dividing that by 12 ends up being 649.11 foot kips. And remember, we already determined that phi is 0.9. So phi mn, I'll go ahead and do that for you. 0.9 times that is 584.2. Is this making sense? All right. Next time what we're going to do is we're going to analyze the next example, which this example, the compression steel yielded. I'll go ahead and tell you the next one it's not going to yield. It doesn't make the example harder, it just makes it a bit longer because the formula gets a little nastier. But fortunately, it's already derived, so it does get to be a little plug and chug. That is all I have, everybody. If you're not in steel, I will see you on Friday.